Relations. 1. Introduction. In our daily life, we have many relations. For example, a student taking Math 500, and then we can say the student is related to Math 500. But how do we use a notation for that? A simple notation can be like this. Student, Math 500. This is a clear but simple notation. And this notation promotes us to define a relation by the Cartesian product. So we may say define S to be the set of all students at TAMUC, and then C to be the set of all courses at TAMUC. Then you know the Cartesian product S cross C. We learned it before. And then student related to Math 500 is just a point. That is one student. But if you talk about all students, then it is a subset, right? So, and then if you talk about the M to be all students in Math 500, and then C is subset. So that's denote C500 stand for Math 500. This is only one course. Then M cross C500 is a subset of S cross C. So this one clearly defines a relation for all students taking Math 500, and then you can consider this is a subset of X cross C. So this promotes us to a more general definition of relation. Definition that A and B be non-empty sets. A relation from A to B is a subset R in A cross B. For each point, because it's a cross product, so for each point, A, B in R, and that means A related to B, and it's a set that A is related to B by R, and also denoted by A is R related to B. So if you look at, say, the picture, say you have set A here, and then you have many points here, and then you have set B here, and then you have many points here, and then you have some points that put together. So you have A here and B here, you put together. That indicates these two elements are related. So, and that is the definition for relation. And then similarly, we also have another definition called domain and range. So let's state the domain and range, then we will explain a little bit. That A and B be non-empty sets and are a relation from A to B. The domain of R is the set of all elements in A such that there is a B in B with A and B together is a point in R. And then the range of R is all elements in B such that there is an A with a B in R. It's important. This is important. So if you look at the picture here, then you have A, and you have A has many points, and then you have a B, and then you have many points. And then the relation is they relate some points in A with some points in B. So that is related by R. Then these points here are the domain, and these points here are the range. Not every point in A is in the domain, and not every point in B is in the range. It must be the points that they related to be the domain and range. That's why in the domain we say there is a B in B, and here there is an A in A. Let's look at an example here. And this example is, in fact, a function we know is a relation, right? Remember the definition of function? A definition of function is that a function is a relation such that it assigns for each x a unique y. So that is the definition. But a relation does not require a uniqueness. For each x, a relation can have many y assigned to x. But for function, you can only have one y assigned to x. But let's look at how we define a function, a relation by a function. For a function, we know x is a real number and y is a real number. So we talk about xy as a point in the real number cross the real number. So this is the Cartesian product of real numbers. So now the relation can be defined by xy, that's a coordinate, and then xy are in the real number set cross the real number set, also y equals f of x. So this will be a relation, and it is a subset of R cross R. When we look at the domain of this relation defined by the function, then you follow the domain of the relation we defined. So A is in A, but there is a B in B. So in our case, then there will be all x. These are real numbers. And then there is a y in the real number set such that y equals f of x. And that all x is called a domain. And then the range of this relation defined by the function, there will be all y in R such that there is an x in the real number set that y equals f of x. So again, not every y is in the range. It's only those y you can find an x to make this equality. Same as not every x is in the range, is in the domain. Only those x you can find a y such that y equals f of x, then those x are in the domain. And let's look at this further. For example, y equals square root x plus 2. So then the definition of the relation defined by this function will be xy such that y equals square root x plus 2. Both x and y are real numbers. So that is the definition of relation for this function. Then the domain for this function, that will be order x such that y equals, such that there is a y in the real number set such that y equals square root x plus 2. So that is the domain for this. But you know, to have a y satisfy this equality, then the square root need to be a real number. So then to be a real number, then x plus 2 needs to be greater than or equal to 0, so that you can be a real number. Then you can, for each y, you can match this. So therefore, x plus 2 must be greater than or equal to 0. Then you further solve this inequality, minus 2 from the two sides, so x is greater than or equal to -2. Therefore, domain can be written in terms of interval notation, -2 to infinity. And then for the range, the definition will be all y such that there is an x for each y, satisfy y equals x plus 2. So that would be, not every real number can be in the range, only the real numbers that you can find an x so that y equals this. So, but for any x, this will be greater than 0. Square root x plus 2 is always greater than or equal to 0. Therefore, the value to make the, so the y to make this equality, then that y must be greater than or equal to 0, so that the range can be written in terms of interval notation like this. When we study relation, we also often study a relation from the A to A. In this case, then we say a relation from A to A is called a relation on the set A. Let's look at an example about this. This example is in the book. Find all relations on U equals 1, 2. So in fact, we talk about a relation from U to U. And this set has only two numbers, two elements. And then remember, we mentioned about a relation is a subset of the cross product. So you actually, when we talk about all relations, to find all relations actually is to find all subsets of U cross U. But let's look at what are elements of U cross U. So this is the Cartesian product. So U cross U, because U have 1, 2, so you can take 1 and then match 1. So this is 1 point. So you take 1 from here, 1 from here, that's 1 point. You can take 1 from the first U, and then you can take a 2. And then you can also take 2 from the first one, and then 1 from the second. You can take 2 and 2. So we have 4 elements in U cross U. And then with 4 elements, we can make a, many subsets. Do you know how many subsets we can make? So this is, we mentioned about before, the power set of U cross U. Because you have 4 elements, so there will be 2 to the 4th power. There will be 16 subsets for this one. So therefore, you may have 16 relations. Let's write all the subsets of U cross U, and each subset is a relation. So first look at R1. That will be non-empty set, as we said before. It's also a subset. So this relation defines no relation between any two numbers. And then R2, let's look at one element relation. So you can have 1, 1. And then R3, you can have 1, 2. R4, you can have 2, 1. 5, R5, you can have 2, 2. So these 4 are one element subsets. And let's look at 2 element subsets. R6, you take 1, 1, 1, 2. And then R7, you take 1, 1, 2, 1. And then R8, you take 1, 1, 1, 2. 1, 1, 2, 1, and then 1, 1, 2, 2. And then you take R9, you finish with this, and then you take 1, 2, 2, 1, this is 2 element subset. R10, you take 1, 2, 2, 2. R11, you finish with 1, 2, and then you take 2, 1, 2, 2. So to see how many 2 element subset, this is a good exercise for combination. So you have 4 elements here. Take 2 at a time. That shows you how many subsets of 2 element subset. And then let's look at 3 elements now. So R12, you take 1, 1, 1, 2, and then 2, 1. And that is a 3 element subset. You can also take another 3 element subset that is 1, 1, 1, 2, and then you take 2, 2. And let's look at another one. So let's move to here. 1, 2. We still can take with 1, 1. Sorry. We still can take 1, 1. And then 2, 1 and 2, 2. And then 15. We take 1, 2. 2, 1, 2, 2. To see how many subsets of 3 elements, and this is combination of 4 elements here taking 3 at a time. So you know this will be 4. So that help you to see how many. And then R16, there will be all 4 elements itself. It's also a subset. So there are 16 subsets, and that means we have 16 different relations. Among these 16 relations, one is kind of special and is R8. And if you put the elements in this format, 1, 1, 1, 2, and then 2, 1, 2, 2, then these 2 points are in the diagonal of this arrangement. So therefore R8, a relation like this, is called the diagonal on set A. And that is denoted by diagonal on set A. So that is denoted by AA, such that A is an element in A in general. Although we use numbers for this example, but each number, you can also replace a number by other objects like students, courses. So then you can see, and this actually, although it's written in terms of number, but it's very meaningful because you can consider numbers are students, or numbers are courses, or numbers are different meaning. So it can be generalized to any other, relations in application. So this is our introduction, and your homework for this introduction is assignment number 43. Thank you.